This is a presentation by Dr. Sharan Srinivas, Assistant Professor in the Department of Industrial and Manufacturing Systems Engineering, University of Missouri, Columbia. The topic of his presentation is machine learning based long-term risk calculator for adolescents. And Sharan, it's a person who really impressed me when he came to me, independently, actually. I don't know if somebody indicated him to come to me, but then we immediately understood each other, what he wanted to do with this type of research, especially with regard to cardiometabolic disease. I think his focus back then was more cardiovascular, and I have moved him a little bit towards my diabetes orientation, but it's very similar. And then we have collaborated a little bit on this because it's mostly his own original idea. But I'm very pleased to introduce Sharan to this presentation. This is a series of seminars that we have in our HIDR, Health Informatics for Diabetes Research group, which is part of a larger grant, P30 by NIDDK, NIH, NIDDK, funded to 3 universities, Washington University, Drexel University, and the University of Missouri. And I'm one of the co-PIs on this grant and the director of the program. Many of my colleagues in my department, including Dr. Popescu, Dr. Suborn, and Dr. Praveen Rao, also, and Dr. Minsum Kim, I'm also participating in this grant, and they are members of this group. So we are a working group to provide consulting and diabetes related research, especially with focus on applied prevention and control of diabetes. And that's related to the topic of our presentation today. So without further ado, I will ask Dr. Sharan Srinivas to start his presentation. Thank you.
Thank you for the introduction, Dr. Sumos, and thank you for the invitation to present today. So I'm just going to share my screen. Okay, all right. So yeah, good afternoon, everyone. I'm Sharan Srinivas, an assistant professor in the Department of Industrial and Manufacturing Systems Engineering at Mizzou. So here's a quick overview or a one-slide snapshot of my experience and my research background. So I have a joint appointment with the Department of Marketing and the Department of Industrial Engineering. I completed my PhD from Penn State in Industrial Engineering in 2017. So most of my research interest and teaching interest are at the intersection of operations research and data analytics. We have a home consortium in the College of Engineering for which I'm serving as the director, which is basically healthcare operations management and engineering analytics consortium. It's got a multidisciplinary team of researchers and health practitioners, which primarily focuses on solving healthcare problems for sponsored hospitals and so on and so forth. In addition, I've done a lot of industry-based sponsored collaborations with a bunch of companies, primarily developing decision support tools, analytical tools, in a easy-to-use interface for them to make business decisions. And as part of this particular research proposal, I have 2 collaborators. One is Dr. Sumos, who has been guiding the research aims and helping me in shaping the proposal. And then we have Dr. Amy Braddock. She's an associate professor of family and community medicine, who's got expertise in adolescent health and so on and so forth. So the agenda for today's presentation is I'll give a quick overview of the proposed research, followed by the motivation and the knowledge gaps, and then highlight the research aims, which seeks to address the aforementioned knowledge gaps, followed by the significance, innovation, and approach that we are proposing. This is part of this is an ongoing work, and then we have submitted it to a few research grants. So I would like to get some feedbacks at the end of the presentation from the participants on where to target the proposed research and how to get it funded. So as you're probably aware, about 1.5 million Americans are diagnosed with diabetes every year, and it's the seventh leading cause of death in the US. And out of these cases that are being diagnosed, majority of them, 90 to 95% of them, are attributed to type 2 diabetes. And this trend is continued to expected to grow in the future. So by 2030, we expect to have about 54.9 million Americans with the prevalence of type 2 diabetes. In addition to having potential harm to the Americans, it also results in significant amount in healthcare cost. It is estimated that it's going to contribute about $327 billion in healthcare cost and lost productivity. And it's also likely to lead to a host of other health complications like blindness, heart disease, so on and so forth. And even though the prevalence is so high, about 50% of these cases are preventable through healthy lifestyle interventions. And most diagnosis or treatment or intervention strategies are initiated late, thereby making the prevention difficult. And many research, there's strong research that suggests that early life behaviors has a long-term impact or a long-term association with adulthood type 2 diabetes. For instance, most individuals who have unhealthy diets or physical inactivity in their adolescence are likely to develop type 2 diabetes in adulthood. Likewise, low socioeconomic status or psychological events like stressful events in adolescence play a key role or have a strong association with type 2 diabetes in adulthood. So there's a strong body of literature that suggests that your early life behaviors has a strong association with the likelihood of developing type 2 diabetes in adulthood. And one of the recent papers has suggested that over 50% of the adolescents do not have over 5+ ideal health metrics. So on the right-hand side in the chart, we have different health metrics that were considered, like the sugar, blood glucose, blood pressure, cholesterol, diet pattern, and so on and so forth. And it was observed that more than 50% of the adolescents did not have an ideal value for at least 5 of them among the 7 health metrics considered. And with this as the motivation, so there's a lot of scope to improve the adolescent behavior. And we also know that early adolescent behavior has a strong association with adulthood type 2 diabetes. So prevention strategies that are initiated early in the adolescence may offer the best opportunity to prevent type 2 diabetes later in life. So that serves as a motivation for our research. And for this, we need a sort of a tool, a periodic type 2 diabetes assessment tool, especially for children, adolescents, and young adults, right? So that they can periodically screen, and based on the outcome of the screening, they can facilitate early intervention and prevention. So currently there exists a tool. The American Diabetes Association on their website has a risk assessment tool, which is based on 7 key factors or 7 questions. And they use the traditional regression model to estimate your risk as high or low. And the 7 factors considered are age, gender, medical history of the family, blood pressure, physical activity, race, and body mass index. So this already exists, but it's also got certain drawbacks. So one of the main drawbacks is that it was developed on cross-sectional data. So it doesn't have the longitudinal association observed in the risk calculator. And then all the samples that were used to develop this particular tool, the risk assessment tool, uses adults over 40+ years. Right? So this makes it, so the suitability of this particular tool for young children or adolescents is not known. So it lacks longitudinal clinical evaluation and considers fewer risk factors, which are more important at the adolescent level, such as psychological or socioeconomic factors, which has a good impact in the adolescent level, and then it is expected to stay or remain the same throughout their life. So in summary, existing risk calculators may not be suitable for determining the long-term impact of unhealthy behavior in earlier adolescent years. So with that, we have the following knowledge gaps in addition to that. So most of the previous work that assess the long-term impact of adolescent behaviors focus on a single risk factor. So they try to see if adolescent obesity has an impact or association with adulthood type 2 diabetes, or does adolescent blood pressure or physical inactivity has a long-term association with type 2 diabetes. So most of them are single risk factor analysis, and studies that consider more than one risk factors typically use different forms of regression or multivariate analysis. So most of these studies assume the risk factors to be related in a linear pattern with type 2 diabetes. Therefore, they do not consider some of the interactions that might be possible. So machine learning algorithms have these potential to overcome these drawbacks. So it's able to automatically learn the nonlinear interactions. So you don't have to explicitly state the interaction variables. It's able to infer the nonlinear interactions from the historical data. And it's also able to identify latent risk factors that may otherwise be ignored. So there's a potential for using machine learning algorithms to develop a type 2 diabetes risk calculator for adolescents. And one of the recent research also suggests that machine learning, a lot of chronic conditions are expected to benefit from machine learning. And as you can see, diabetes has the highest score. So the most benefit is expected to be for diabetic care, followed by heart disease, and so on and so forth. Another important aspects to consider in machine learning is the fairness of the algorithm. So machine learning models are capable of learning the bias from the data. So if your data's got some sort of a bias, then it's going to learn that bias and then make predictions that are biased. So in order to avoid such biased prediction or biased learning, it is important to incorporate some effective strategies that can mitigate these risks. So for instance, if there is some sort of inherent bias in your data or learning mechanism, then the model may overestimate the risk for an individual belonging to a a specific ethnic group, such as African Americans, due to the high prevalence of type 2 diabetes in such groups. So another important aspect to consider is to create a fair or equitable machine learning model. So that brings us to the aims of the proposed research. The first aim is to develop a fairness-aware machine learning-based calculator to predict the long-term risk of adolescent type 2 diabetes. So are we able to predict the risk of an adolescent 30 years into the future? So when they become 30 for 50 or 60, are you able to predict how their risk is going to be and identify the factors that could be changed so that their risk can be lowered? And in the first aim, we're seeking to use the same risk factors that are considered by the American Diabetes Association as inputs for the machine learning model, and compare its predictive performance to the existing model that is developed by ADA. The second one is to see if we can examine a more comprehensive set of factors. So based on the literature, recent literature, we have identified 14 new factors that pertains to lifestyle and psychological behaviors of the adolescent. So in addition to the 7 ADA factors, we have 14 new factors based on recent literature and expert opinion. So can we take these 21 factors and see if there is an improvement in the prediction accuracy of long-term diabetes? And the third aim is to assess and comprehend the predictions produced by the machine learning algorithm. So are we able to explain the prediction? Because it's very important in a healthcare setting, because physicians or clinicians are hesitant to just rely on the machine and make a decision. So you want to be able to explain on why a certain individual was predicted as high risk, or why an individual was predicted as low risk, and what factors or what inputs could be adjusted to improve or lower the risk of this particular individual. And to do all these three aims, we are going to use the AdHealth data set, which is a nationally representative sample of individuals from adolescence to adulthood. So this study basically surveyed individuals for over 20 plus years, and then in multiple waves. And on each wave, it collected did some survey questions to collect their feedback on certain attributes of their life, like their diet pattern, or how much sort of risky behaviors they have, like smoking, use of marijuana, so on and so forth. So this has a survey type mechanism, and also did some health test for these individuals at different waves. So in wave 4, for instance, they did the blood test to see their actual level of diabetes. So we have both the set of inputs in the adolescents, and also the uh, event, the diabetic event in wave 4 and wave 5 from this particular data set. So the significance aspect of this research is that there's potential to generate new scientific knowledge on the feasibility of accurately and fairly predicting the long-term risk of type 2 diabetes. And it also has the potential to do an early detection and targeted intervention of individuals based on the risk predicted. And it's easily has the potential to transform other chronic diseases such as cardiovascular disease or obesity and so on and so forth. Finally, successful validation of this particular approach or risk calculator would drive the use of ML and interpretable AI techniques for risk prediction, longitudinal analysis, and targeted intervention. As far as the innovation of the proposed aim goes, we have the following four. It applies to the adolescent population. Like I mentioned before, existing risk calculators may not be suitable for adolescent population. Therefore, this current tool is applicable to adolescent population because it is trained using adolescent samples. And then it's also has the long-term risk prediction capability. So you can predict a 25-year type 2 diabetes risk for adolescents using longitudinal data, as opposed to the cross-sectional data that's used in most of the existing risk calculators. And it is unconstrained because we are not using regression models, we are using sort of machine learning model. So it is automatically able to consider all possible sorts of interaction or relatedness of risk factors and its incidence on diabetes. Finally, it would consider fairness in model prediction. So you'll ensure predictive parity so that it doesn't overestimate the risk for one group and underestimate the risk for another group, with the goal of advancing health equity. So the research methodology, like I mentioned earlier, we are going to use existing longitudinal data set. It's got from adult study, which was conducted over multiple waves. It includes over 20,000 individuals as samples in wave 1. And due to attrition and dropouts, we had about 16,000 samples in wave 4. So those are the two waves that are primarily being used to develop the machine learning model. And this is the workflow of the proposed method. So you have the data, and then do a sort of pre-processing and feature engineering. And after that, the data is split into training testing, train the algorithm, and ensure that it's incorporate fairness in the loss function, and then validate it, and then understand the impact. So we have the three aims integrated into the workflow that's shown here. We can look into the details, specific details in the upcoming slides. So the predictors that we have identified so far are primarily from wave 1 data. In this, the average age of the uh, um, program participants was about 16 years. And we are trying to focus on different categories, starting from demographics, socioeconomic factors, lifestyle choices, health risk, and psychological. So all the factors that have been identified are based on the review of literature, and also the availability of the data in the survey questionnaire. So some of the surveys, so some of the variables were not available, and therefore we are limited by those things. But we were able to identify about 21 factors that could have an influence, or that could help us estimate the long-term risk for type 2 diabetes. And the outcome variable is basically obtained after a 25-year follow-up test in wave 5. In this time, the average age of the participant was about 40 years, and it's classified as normal, pre-diabetic, and diabetic. So it's a classification problem. You want to predict if there is a high risk of being diabetic, high risk of being pre-diabetic, or there is low risk of being diabetic. So that's your outcome variable. and your input variables or the predictors are the following 21 variables. And all the variables with a star here denotes the variables that are currently used by the American Diabetic Association for risk assessment. So with regards to pre-processing, we intend to do the typical procedure of validating, coding, cleaning, and transforming the data to ensure that it's suitable for machine learning, and different sorts of visualization and will be done. And one important aspect that we'll do is try and create meaningful variables. So the survey question might have 10 or 20 questions on diet, and we aim to do a factor analysis and combine these survey items into one variable, capturing a dietary pattern or physical activity. For instance, with respect to psychological factors such as depression, this survey by AdHealth includes the scale items from the CESD scale, the depression scale. So that's a validated scale, and we can directly combine questions pertaining to those items, questions pertaining to depression into one variable. So that will also be done as part of pre-processing to limit the number of variables that are being used and to avoid potential multicollinearity issues. And then the process data is further split into training and testing for development of the risk calculator. And a bunch of algorithms will be trained since it's a new set of data, and it's one of the first work to try and predict the long-term risk of type 2 diabetes. It's not clear on what patterns the data could exhibit. So we aim to develop different algorithms which have different learning mechanisms. So a sample of these algorithms are suggested here, which has shown to produce promising results on other risk prediction, for example, for prediction of heart disease and so on and so forth. These random forest and rare gradient boosting have shown good performance. Therefore, based on the review of literature and our own experience, we have proposed to train and test 5 different algorithms. Optimal classification tree is one of the new machine learning algorithms, which offers high explainability and a performance equal to the random forest or gradient boosting. So random forest and gradient boosting, as you know, are black box algorithms. So there's lack of explainability there. Optimal classification tree uses mixed integer programming and game theory to train from the data, and then offers an explainable output without significantly compromising on the prediction accuracy. And to account for fairness in model, we were aiming to develop a loss function, integrate a loss function into the training mechanism that imposes a higher penalty for overestimating or underestimating the disadvantaged groups. And to ensure fairness, we will seek to prepare the data in such a way that the risk factors are not overly disproportionate among the different groups. So we'll sort of use oversampling and undersampling techniques to generate a fair data. In addition, we'll also ensure fairness in model development through a loss function. And with respect to evaluation, we will use the testing data set and use most commonly used metrics for classification problems such as AUC, PRC, FN scores for each of these classes. And in addition, we will also use predictive parity to ensure the fairness in the prediction of the algorithm. So is it able to predict is the accuracy, for instance, of the different groups very similar, or is the accuracy higher for Caucasians as opposed to African Americans, so on and so forth. So we'll also use predictive parity to evaluate the fairness of the algorithm that's developed. And then the last aim is to understand the predictions or explain the predictions. So logistic regression models or the optimal classification trees that are being developed are self-explainable models. So they themselves tell you how they arrived at the predictions. On the other hand, other methods proposed, such as deep learning and random forest, require some post hoc explainability to understand the predictions. And in this case, we are planning to use Shapley additive explanation. So which is again a game theoretic approach to explain the output of these black box ML algorithms. And we have also anticipated potential problems that we may encounter. For instance, one of the common problem that we may encounter is the high dimensionality in the data set, which may likely introduce spurious correlations between the independent and the dependent variables. So to overcome that, we'll use the standard practice that's been adopted in the machine learning literature. So try to reduce the dimension of the data set, use cross-validation for training, include a large sample, and then do a good pre-processing to remove errors and obtain an unbiased sample. So if this risk calculator is successful, then we evaluate success in terms of its ability to predict at a greater accuracy than the existing risk assessment model. So that's how we want to evaluate the success of the proposed machine learning model. And as a next step, we have two different approaches. Once the model is successfully developed and evaluated on the testing data set, we intend to validate this risk calculator on MU healthcare data. So where we aim to retrieve 20 years of longitudinal data starting from 2003, and then the outcome will be extracted on 2023 from the EMR data. And with this 20 years of longitudinal data, we intend to do an external validation of this particular risk calculator. And another direction of future research is to use this risk calculator. We also want to like evaluate the causality among the different subgroups so that we can enable personalized intervention strategies. So that would help us answer certain questions like what would be the type 2 diabetes risk for a person if he or she did not smoke, or was it the lack of physical activity that led to high type 2 diabetes risk for an individual, so on and so forth. So that is also a part of our next step. So yeah, that completes my proposal overview that was prepared for developing a machine learning based risk calculator for type 2 diabetes. So I'll be happy to answer any questions and hoping to get some feedback from the committee.
Thanks, Sharan. I'd like to make a comment. That was an excellent presentation, first off, and just to remind those participating that one of the main aim of this presentation is to get feedback from you on how can we improve what he's presenting as we write a grant application. I think it's a very strong research subject. It's very innovative in a way, but more important, it's very significant. Diabetes is a big problem, and predicting early is the key to change. We know that, but there's no good tool out there, and this could be very innovative and very important for practice of primary care and prevention. So again, just think about not as a research or paper that it needs to be published, but as a grant application. What are the things that in this presentation that still need to be highlighted, or additional things that need to be shown in this presentation that we can take it and write a grant with it? And I will start with a general question about how do we envision, Sharan, for this score to be used in practice? What is the score that you're trying to get out of it? And you did not show in your presentation some ideas about once you have an index or a scale that you can be used, what additional research is needed in terms of showing the reliability and the validity of that score. So that's something I didn't see in the presentation, but we could elaborate a little bit more. But please, folks, feel free to ask more questions. I just asked this one. Do you want to go answer one question at a time, or you want to collect all the questions and then you're trying to answer them all? How you want to go about this, Sharan?
I can do one question at a time.
Okay, so my comment is, how do you envision that being used in practice? If you have that vision, if that's needed to put in a grant, I think it is. But the other one is, once you have a scale or an index or a score that you created out of this research, what are the additional research that you think may be needed? Maybe we put that in a grant right now.
Okay. So initially I was thinking of like having a similar application to the ADA risk assessment tool where you have a web page or an app that lets the user input their input variables, and then the model predicts an output score. And it can also be used by clinicians to evaluate the risk of adolescents. So that's where like Dr. Amy Braddock comes into play. So she had some ideas on how she can take that into practice. But before we do that, like one of our key next steps is to do an external validation. So to make sure that the model that we developed, train and tested is suitable for other similar data sets.
Yeah, I tell you what I was expecting to see. You gave me the chance to review it, but I wanted to leave without the corrections because I wanted you to be able to answer thoughts so I can see everything it's very strong. I understand exactly what you're going to do, and the word risk it's thrown here and there, but there was no. Usually in medicine, when people talk about a scale or score like the Framingham score for determine if you're going to have a chance to develop coronary heart disease or any cardiovascular related event out of a score that you take it based on a few factors. Usually this is emulated the risk analysis of the research because this is different. This is machine learning, and you did not specifically mention what's the outcome measure. It would be interesting for me to see something in terms of relative risk or risk to say, this score, what you expect to see is after you hit a score of such value, then your risk goes up by much, okay? Or the relative risk goes from 1 through 2 and then to 3 to 4, 5. You double your risk, something like that. So that's missing on the presentation. That I think is very important for people who are going to review this to understand how you're going to use this in practice. So you're trying to get a score to say, oh, you have just a greater risk, and you get a beta coefficient like in a regression, or you're going to say, no, this score we try to extract here is not only you gotta have a risk, but I will have a measure of that risk, okay? And that measure you're going to tell is if you go from here to here, and if you change those factors, you may reduce your risk, but from X to X. You with me?
Yes. So right now I have three variables. It's a classification problem. So the outcome variables are like normal, pre-diabetic, and diabetic. So I was thinking like if the long-term prediction is normal, then the risk is low. Pre-diabetic is moderate risk, and diabetic is high risk. Is how I thought in when I was writing the proposal. And then when we use these like AIM3, the explainable methods, we'll be able to see the counterfactuals and tell what can be changed for that individual so that their risk goes from higher to moderate or higher to low risk.
Okay. It's not so clear in the presentation.
Okay.
You can add.
I'll update it in the proposal. Okay.
Yeah. So you can look into when you write, you could use this as a guidance to your writing. That's why it's so good to make a presentation to the group so we can actually change that. So I'll give a chance to others to have other questions.
Hi, this is Moshkan Korsi. Nice presentation. I have one question. Um, I see that you have different type of variables like gender, which is binary, and the continuous variable. Do you do any kind of standardization of the variables or some kind of weighting? If the machine learning is
so the variables will be normalized before it's being trained. So it will be standardized. Weighting aspects will be considered for the outcome variable to ensure fairness. So if there is a certain disadvantaged group, we are planning to weight that in the loss function so that the penalty is higher when an incorrect prediction is made for such kind of groups.
Thank you.
Yeah.
Sharon, I have another question. You you have mentioned another score for adults, especially used for people 40 plus that tries to do that job. So it is kind of a nearly clear, but not so clear. You're going to replicate that before you actually apply your machine learning to using the 21 variable, but you're going to replicate the existing model. But then now, instead of being with adults, it's going to be in younger person. Is there any different way of doing that? Do you think you need to try something different, just because it is not the same crowd, the same population that generated the other type of index? You're now using much younger population, exactly 24 on average, 24 years younger. Don't you think that this is not a kind of fair or comparable type of it? It's not totally comparable, even though you're trying to replicate. That's what you said.
Right. The reason for choosing the ADA tool is because that's the existing tool. There's no specific tool for adolescents. So if right now this is what is being used, so the ADA tool has a category called less than 40. So even if you're adolescents or even 35, 38, any age less than 40, you choose that category when you're evaluating the risk score. So ADA tool right now allows adolescents to estimate their risk, but it is not designed for that. So to show that the benefit of using machine learning, I was proposing to compare it with the existing tool, but I have not thought about how to like tweak it to make it more suitable for adolescents.
I hear you. Okay, makes sense. Except I just will have one comment about the ADA. They will use cross-sectional data to create their tool, their score. So their estimation of risk is not really a risk. It's actually prevalence, which is a different animal. It's related, but it's a different thing. Here you definitely have the longitudinal view. You could have the option, for instance, instead of doing a machine learning, to do a traditional multivariate regression and not be I would say just linear. It could actually be way better than linear, in a sense that yes, they are linear on the approximation, but they are also accept different type of situations. You could use a multivariate regression for a Cox model for survival analysis, because you have longitudinal data. You have wave 1, wave 2, wave 3. You can, in every wave, you can estimate the change from baseline to follow-up, any follow-up period, and you can estimate the percent time of each of these people and come up with a similar prediction, but it's just a traditional regression model. Okay. And so you explained to me before and now in the presentation why the machine learning would be something to be thought of. But a Cox model could do that job, or even a Poisson regression model, because you have count. You can consider these to be count, and you can estimate the risk in one group, the new event arising over time. It's the risk, okay, out of the total denominator at baseline. So that's estimation of true risk, not just a prevalence like they did in ADA. Mm-hmm. So make the argument with me about machine learning. It's still not totally strong for me.
Okay. So, so what we have observed based on our preliminary analysis is regression models do not offer higher predictive accuracy for the testing data set. So we replicated this for I have it in the preliminary study where we tried to replicate this for cardiovascular disease using the same data set, and we were able to obtain good performance for machine learning models as opposed to traditional regression models. So that's one of the main reasons of even many prior works have shown that risk prediction using regression is not very accurate, because you're trying to predict at the individual level and not trying to get the characteristics of the whole population. So that's one of the main reasons for machine learning, using machine learning. And we don't know if machine learning will be better than regression, to be honest. So that's why one of the aim one tries to evaluate if it's actually better than using regression.
Yeah, well, I think this is the most salient point for a grant, Sharan, because you're just said I'm not sure. So why would you convince me in a panel in NIH that I need to fund you to do something you're not sure? You see what I mean?
It's mostly based on preliminary work. So the preliminary work which was done for predicting long-term heart disease, using the same data set, adult data set, adolescent and adult population, showed that machine learning outperformed regression significantly.
Okay, that didn't come across on the presentation. See what I mean?
Yeah, I didn't
Oh,
put it yet. Yeah, so I
uh,
just, in interest of time, I put it in the preliminary works, which it shows like the performance of.
okay, yeah, that could
Yeah.
be part of the presentation. Because I would like for your presentation to be what a guidance to the grant submission, you know?
Mhm.
So that's a powerful statement. You have data before, you look at CVD, similar idea scale. CVD has another standard scale from Framingham studies done for 50 years now. And then you have, compare the regression-based prediction, which are poor compared to a machine learning, which are more, explanatory and more predictive, so to speak. So that's a powerful justification there to be part of the rationale, because it was part of your motivation,
Mhm.
and I don't think it was that clear there.
Okay.
So, folks, I'm asking too many questions. Please go ahead. Anybody else?
Mm. Can you hear me?
Yes.
Okay, I'm Arur. I work in endocrinology. I was curious that what about the newer markers or something? If it is added up, can you incorporate that as a part of previous study plus the prospective study, something like that?
So our training is mostly, right now, the way it's designed or written is, the training is mostly dependent on the availability of data for
Okay,
that specific individual in the survey item. So if it's not, if those sort of markers are not available in the existing questionnaires or
got
health
it.
test, it's
Yeah.
difficult for us to incorporate.
Sharon, I have another topic for maybe hopefully the group can ask question too, or make a comment on my comment. Is that you started the presentation and your rationale for having this research saying that you're trying to find a score that predicts that diabetes development in the future. But I wonder if there would be more powerful from a funding perspective if you had framed that as predicting pre-diabetes, okay, which is like metabolic syndrome. And I don't know if you have that in your data. Why? Because this is people at risk for diabetes, younger adults at risk for diabetes. But if you are in the adolescent, you may not even be at that risk. You'd be extremely normal, but you have already the fundamental behavioral change that's going to lead you to be at risk for diabetes and then fully develop diabetes. So this is a kind of a more maybe philosophical, but also practical perspective. And if you have data on your data set, I want you to consider predicting metabolic syndrome, which is a pre-diabetic process, because that becomes even more powerful from an economic primary care prevention perspective, because you're really being very early, being able to intervene. But bottom line is, let's say you have a person that's extremely normal, age 16, very healthy, no metabolic syndrome, and you can predict metabolic syndrome in 6, 7, 8, 9 years later or 10 years later. That's more powerful than predicting total diabetes along the lines, and you can also do such a way that you can predict the pre-metabolic phase, the metabolic syndrome and the diabetes with the same set of predictors, and do both. We're going to do both anyway. to see how powerful this thing can be.
Okay.
I don't know if it's, so do you think you have data on there for? Do you
I
have
need
it?
to check on that. Yeah, I'm not sure.
Okay.
The more folks, the more you ask questions, the more it gets better.
I think it is. Yeah, I do agree with the doctor's the comments on pre-diabetes. Actually, in fact, there is a very recent article came, Sharon. You can look into that. All people are trusted so far on fasting blood glucose. Now they are telling that after 1 or 90 minutes or 60 minutes after food or breakfast, that may be more index of a future diabetes or the disturbance. I think you can include that. Easily can be done, but it can be add a one more component which is compatible with the people and other things. Something like that. I think I agree with that. Pre-diabetes or detection before manifestations may be more is a very novel, I believe, because that was the one actually can detect, or the one example, if you want to put that way, is all the diabetic will never develop hypertension. Only 40 to 50% will develop. What that differentiates from all the rest of the group, because that makes a big difference. If there is a BP, yes or no, that determines later whether they are going to develop kidney disease or not. So in other words, it is like a early, and second thing it is coming up is nobody has got a basal value like a 20 years or 30 years back. Suppose a fellow comes 50 years, we say, oh, his BP is, it is near normal. But suppose his BP was like 100, say at the age of 40. Now 110 is 10% higher for him, which is maybe detect. I think if you bring some kind of that, I am not able to explain, but I think that was the pre-diabetic component may be more meaningful, I believe, very strong component, I believe.
Okay.
Yeah, so Sharan, for you to diagnose, predict that pre-diabetes or syndromic type of view of diabetes, you would have to have measure on the the waves, the cohort follow-up, baseline and follow-up of HDL, for instance, high density lipoprotein, triglycerides, blood pressure. I know you have it in this
Yeah.
data set. Surely you have the sugar level. That's what
Mhm.
determines the diabetes. Probably you have A1C measure. But the other one that may be missing in the data set is the waist measure. How to, I don't know if you have in the data set that waist measure, because it'll be interesting from a funder's perspective, NIH, to be able to predict metabolic syndrome, because that's very powerful. And as well as diabetes, I think both. If you could, it would be better, like I said. But you have, it's a bunch of other variables, very interesting and easily collectible, and most people have that information available in medical records that you can be used in adolescents to come up with a measure of their risk of developing, hopefully, metabolic syndrome and certainly type 2 diabetes. So that's the goal. But these are the main 5 issues. There's a waist size, that's 40 inches for men and 35 inches for women, but this is for adults. So I don't know if there's a metabolic syndrome for children, but we could apply the same because these kids are so large, and average age is 16, and pretty much in America at age 16 you're an adult physically, especially here. Abnormal blood sugar level you have measured, blood pressure, triglycerides, and HDL, more specifically, high density lipoprotein. So
I may have missed it. Do you have family history of diabetes in the data
Yes.
set?
For
Okay.
the adolescents, yes, we do have them.
but is that one of those that you have in your prediction model?
Mhm.
Can you bring back the prediction, the 21 variables? You just, yeah. Yeah, also has some psychological.
So here we have parental.
Yeah, you have blood pressure, you have BMI, parental obesity, physical disability. Interesting. There's a good research from Dr. Mary Sadula showing clearly that parental obesity is predictive of the children's um, obesity level in the future. It's amazing. Sleep habits, diet, physical activity, substance abuse, smoking stuff. Yeah, these are many of the things collected regularly on primary care setting. Um, Maybe not so much parental obesity, but they will be in the records for most parents. Not maybe not for all the kids, but most parents. Substance abuse, a lot of that is reported to a primary care type of general. But maybe the thing this thing can do also, Sharon, is to educate primary care physicians to be aware that they need to be collecting this type of information. It's non-intrusive. I don't need to take anybody's blood. I don't need to do any sample, any biopsy or anything like that. Just questionnaire. People answering why they're waiting to see the doctor, these general questions. Some of them are in their natural record. So I think the beauty of that needs to be highlighted in this is that there's no intrusive or invasive type of clinical enterprise to identify adolescents at high risk for diabetes, hopefully for metabolic syndrome too. These all can be collected well, I would say 80% of them already collected in any primary care clinic in America, good ones, but maybe not positive mood or a stressful life event. So you may allow people to start thinking, oh, I want to introduce this in my assessment of primary care for adolescents, for teenagers. If they come for whatever, we can apply that. So that's another use of this model, is to change the clinical behavior,
Right.
to be aware that having this information allow me to do something more powerful than just finding out if the person has a positive attitude about life, is depressed or not, but also it allow me to see if the person has a greater chance of develop diabetes in the future, and they need to be more aggressive in returning that to normal. So I think this message has to be quite loud and clear in the motivation and the applications. That's a rationale for this study.
Okay.
What about the comorbidities? Is there any comorbidities that is related to the diabetes, like kidney, for example?
Sorry, can you repeat the question again?
Is there any comorbidity that may affect may predict the diabetes? For example, kidney disease or anything?
So so in this particular data set, when they were adolescents, there weren't many large number of samples with kidney disease or heart disease. There were few samples with physical limitations, but most of them did not. They were mostly healthy adolescents,
Okay.
or they did not have any like chronic conditions.
Yeah, well, I'd like to make a comment on that, Mojan, is that the knowledge that these risk factors, not all these, but many of these risk factors cause diabetes, it's already there. We know that.
Okay.
We already know there's a risk increased associated with some of those risk factors, especially obesity. A young child or even a teenager obesity has predictive power over their ability to develop diabetes. And that may not have come too clear, Sharon, also in the presentation. You need to say that we already know a lot about that. But what we're trying to find is a useful tool that during the screening process, we can clearly and easily identify people at risk for diabetes early in the stage. So that message is not clear, because people start thinking we try to understand. No, we're not trying to reinvent the wheel. The wheel is already there. We know very much, I would say 90% of the reasons we have diabetes, type 2 diabetes there is. And it's a lot to do with imbalance in your metabolic intake and your expenditure. It's to do with physical activity, diet, and the level of BMI or obesity, or any form of measurement of overweightness and obesity. So we know that, and many other factors in different research have shown to be associated with the risk increase of diabetes. So any individually, but not as a group, not as a set and as a score that can be used to predict. And that's what the research is all about. It's not so much of finding what causes diabetes, but it's like we know these things are related to diabetes. Some of them are being shown to be causal, actually, but can they be used to predict? And can I use this to predict? And then came the other question I asked early on, Sharan. After you do this research, you need to also do another research that's more statistical level to say, out of these 21, maybe I could do away with 5 or 6 of them because they do not have so much weight in increasing the risk equation. You know what I'm saying? They could not add too much. That's a different type of research. It'd be like factor analysis, something like that. You got a scale. You're going to have a scale that you can say risk increase or not, and be a 1, 0. And it can add up the score. 21 is to be total score or something different. Whatever it is, you can do research in the end to simplify even further and still be very, very predictive of what is going to be.
Right.
So
Thank
I
you.
think
That's
that is
very
not.
nice talk. Thank you.
Yeah. Okay. I thought I had clarified that. Folks, we're getting to the very end of this. We have 2 full more minutes. Anybody have any other question that could help Sharan to do a better job on writing a grant on this? Anybody can suggest what type of grant we should be submitting to for this? I'll throw the question a different way to the group. Do you all think that there's a lot of pre-research done on this, not by Sharan himself, but by others, that almost like preclude him to do some of that pilot research done? Like I told you, many of these risk factors have been identified as associated with increased risk of diabetes. But does he need to do a pilot on this before he submit a grant? And if not, do you think an R01 is the right application for this type of grant? Do you have a chance, or should be an R21? Any comment that anybody want to make? It would be helpful. I have 4 minutes to go.